In these last four examples, you're now going to be solving logarithmic equations. And when you solve logarithmic equations, in order to eliminate the log by essentially converting it into an equivalent exponential statement, you need to have a single logarithm on the left-hand side or the side you're trying to isolate the variable on. So in many cases, you're going to have to use the logarithmic properties to combine multiple logarithmic statements into a single logarithmic statement. And as long as you have either a single logarithmic statement equaling a number or a single logarithmic statement equaling another logarithmic statement with the same base, then you're able to do the problem and solve the equation by writing it as an equivalent exponential statement. So for here, having two logarithmic statements being added together, you're not able to clear away the logarithm quite yet. So this needs to be combined into a single logarithmic statement, and from the properties that were discussed earlier in this lesson, the log of x plus the log of 2 can be rewritten as the log of 2x. And so the log of 2x would equal 5. You can rewrite this statement as exponential with a base 10, because this logarithm is base 10. So you would have that 2x would equal 10 to the 5th power. And of course, 10 to the 5th power is 100,000. So if you now divide both sides by 2, you would have that x equals 50,000. In a very similar fashion in the next problem, now you have the same left-hand side equaling the log of 5. So this one here, these situations are actually a little bit easier. Once you get this combined into the single logarithmic statement on the left, which is no surprise, it's the same thing, the log of 2x. Well, if the log of 2x equals the log of 5, and these are the same logarithmic base, then it stands to reason that 2x would have to equal 5. Because the only way to get a logarithm of one thing to equal the logarithm of the same base of another thing is for those two things to actually be the same thing. And then, of course, to solve this equation, you would divide both sides by 2. So you get x equals 5 halves, which is the same thing as saying 2.5. You can write it in decimal form too in some cases. Sometimes the fraction is more desirable if you have to round your decimal places, or if you're told to round to a certain number of decimal places, then obviously they want a decimal answer. For this situation here, it works the same way with the natural logs as it did with the logarithms. Here, you have the natural log of 9 minus the natural log of x equaling 7.57. You want to get this left-hand side to be a single logarithmic statement first. And so since you have the difference of two logarithms, that could be rewritten as the natural log of the quotient of 9 divided by x, and that equals 7.57. Now that you have a single logarithmic statement on the left, this can be rewritten as an exponential statement. And because this is the same thing as log base e, you would have that 9 over x is equal to e to the 7.57 power. Now, using your cross multiplication, this is kind of considered to be over 1. You would have x times e to the 7.57 power equaling 9. And then you would divide both sides by e to the 7.57 power. So 9 divided by e to the 7.57 power would be the exact value for this, and if you approximate that on a calculator, you would get about 0.0046. So that's the solution rounded to 4 decimal places. On the other hand, if you had the natural log of 7.57 on this side instead, again, this would turn into the natural log of 9 over x equaling the natural log of 7.57. Since these logarithms are the same base, they're both base e logarithms, for this to be true, 9 over x would have to be the same thing as 7.57. And so when you do your cross multiplication, you would end up with 7.57x equaling 9. Dividing both sides by 7.57, you get approximately 1.1889. And so that is the end of this problem, and that is the end of this video. If you have any additional questions, please make sure to bring them up during our class session.